In the last video, we looked at the inverse of exponential functions, and I wanted to take some time to look at inverses of other kinds of functions. For instance, any relation, any coordinate plane where I have points on that plane where the coordinates of the ordered pairs are reversed, that's an inverse. So here I have a relation that's only got 2 points on it, but my points are 1, 5, and 5, 1. And notice that if I just folded over my y is equal to x line here, remember that y equals x, that gives us an axis of reflection. If I just folded over that line, then my points would line up. And let's see how that works in a larger sense. Let's take a look at a quadratic function, one that includes this point here, 1, 5. So if I put the vertex of a quadratic at, let's see, 5, 2, 3, 6, 7, 8, 9. If I put the vertex at 3, 9, and so if that's the vertex, then I have an axis of symmetry going through there. So I have a point at 1, 5. Then I have a point here at 5, 5 also. And basically, it just goes down from there. So I have a downward facing parabola that passes through those points and works its way down into the abyss, right? So that's my parabola. That parabola happens to have the equation y is equal to 6x minus x squared. It just goes down. I have a scalar of -1. And on we go. Well, if I were to draw actually the inverse of this equation here, which would say something like x is equal to 6y minus y squared, then we can try and find y at the vertex for this one. Y at the vertex would be -b over 2a, so it would be the opposite of 6 over 2 times -1, or 3. So y at the vertex would be 3. So if y at the vertex is 3, then x would be 6 times 3 minus 9. That would be 3 squared, right? Or 18 minus 9. So x would be 9. So my vertex for this inverse of this downward facing parabola would be at 9, 3. So that goes, here's 5, 6, 7, 8, 9, 1, 2, 3. And notice that's the inverse of this point here, 3, 9, right? Here's a point 5, 5. And here's a point 6, 0. And here's a point 0, 0. So what would happen if I tried to do inverse points using this one? Let's see, instead of 1, 5, I would have 5, 1. And then I also, again, I have my 5, 5. I have my 0, 0. So then I would have my 6, 0 up there. And so my inverse parabola is an exact replica of my original parabola. But if, remember, again, if I fold it along this axis of reflection, notice that my vertices would meet each other. They would just fold up to that one, and the whole of the parabolas would line up. A couple things to remember about this situation, these inverses, is that while the blue one is a function, it's a function because I have one and only one output for every input. I would pass a vertical line test, meaning if I drew a vertical line through any point of the parabola, it would only ever touch the parabola in one spot. Notice that the red one does not pass such muster. The red one is, in this case, not a function. If I were to pass a vertical line through it, I'd be touching, other than the vertex, I'd be touching the parabola at 2 points. Here you can see I have 5, 5. and 5, 1. That doesn't work. I have 0, 0, and also 0, 6. So the red one is not a function. The blue one is a function. The blue one as a function, unfortunately, is not a one-to-one function. So blue is a function, but it is not 1 to 1. Meaning, if I were to do a horizontal line test, notice that I would cross my function twice. If I did a horizontal line test and it only touched the function in one place, say my function were linear, it were a line, say, and I drew a horizontal line across that, I would only ever cross at the one point. This line would be a 1 to 1 function. So that's a little bit about functions and their inverses and the difference between a one-to-one function and a not one-to-one function.